and then for a degree of lower intensity to the others. We had a nice discussion about Lucio Russo forgotten revolution. I am more extremist than Gian Pietro about it. And we had a long discussion about mathematics and the use of mathematics in applied sciences. And important, I appreciated greatly Gian Pietro telling, I do not know this, I do not know that. Also in this school, he admitted to have said something wrong the day before. This honesty is to be respected, in my opinion. This presentation was in a part inspired by him. I don't know if he will recognize. I was attacking a problem using differential geometry in Gaussian way, and Gian Pietro said that in his opinion this was too complicated. I was using a too complicated tool for a problem which seemed to him to be simpler. And indeed, he was right. So a part of the presentation is directly a consequence of a discussion with him. Of course, he will not even agree now, or maybe he will not recognize the point, but this is. No. Look, I follow your indications, and we attacked the problem in Cartesian coordinates. So it should be rather easy. Okay, so the paper I would like to talk about is a joint work with Pierre Seppecher, who got the prize Levi-Civita last year, and Angela Amadeo, who was a previous PhD student of mine, and as many Italians, emigrated à l'INSA de Lyon, where she got a tenure, being less than 30. In Italy, if you are not 45, you never get a tenure. Okay. I want to talk about an old problem. You have a continuous body, and you want to talk about contact actions. Everybody may believe that all problems in this field are already solved. Indeed, this is not the case. My first studies in the subject were originated by the reading of a masterpiece in the field, Paul Germain's paper of '72, written in French. Somebody says that something written in French is not a paper to be cited. And this was written in English, a series of papers of Middlin, Rivlin, and Green. Also Tupin attacked the problem. When you have a continuous body, inside this body, following Cauchy, you imagine that there are contact actions through Cauchy cuts, and these contact actions usually are represented in terms of a surface density of force, small t, the so-called Cauchy vector, and by means of the celebrated tetrahedron argument, it is proven that there is a tensor field, capital T, by means of which you can represent this vector. N is the normal of Cauchy cuts. Actually, historians of mathematics could tell you that tensor, that is a linear function mapping vectors into vectors, is a name who comes from this physical application. Now, what is an nth gradient continuum following Middlin or Rivlin or Germain? It is a continuous body in which deformation energy depends not only on the gradient of displacement, but also on second gradient of displacement, nth order gradient of displacement. Using a French expression, a maladroit use of the principle of thermodynamics led many people to conclude that this continua cannot exist. While Tupin already stated, which is rather strange, in Tupin's Truth del Book, you find in different pages, most likely depending on the author who wrote that page, two contradictory statements. In the part of Tupin, you find a careful treatment of what was known à l'époque about n-gradient continua. Okay, now a Cauchy cut is a surface of material particles on which contact actions. Remark, I'm not using the word force. I'm using the word action. Are assumed to be concentrated. Contact actions must depend on the shape of Cauchy cuts. In nth gradient continua, contact actions can be concentrated on edges and wedges. So if you have a not regular Cauchy cut, you have edges and wedges. You find on these geometric entities some contact actions. Contact actions depend on the shape of Cauchy cuts. Of course, this is like a little bit the series of theses I want to prove. Which one? Yeah, I wrote 2 times the same thing, sorry. Yeah, I wanted to tell it 2 times. Okay? I need to tell it because it is a rather difficult issue to define what is a shape. Okay? So, in a paper of 95, which I wrote with Pierre Sepecher, and the unknown reviewer of it I discovered later was Antonio Di Carlo, to whom many of the results of that papers are due. At least he obliged us to get these results. In that paper, we start with this very weak definition of shape. If you have 2 surfaces, and you have x1 and x2, which belong to these surfaces, sigma 1 and sigma 2, the shape of sigma 2 is the same as the shape of sigma 1 in the corresponding points. If this relationship holds, x2 belongs to the image under a translation of a neighborhood of x1 intersection sigma 2, and this set is a subset of sigma 2. So remark, we have only translations. We do not have rotations. So you have an equivalence class of shapes. I mean, a shape is an equivalence class. There is an equivalence relation for defining shapes. Okay, now for remaining inside the time, or even earning some money, time, which is the same sometimes, we assume, I will go quickly, we assume that in nth gradient continua, contact actions depend on the shape of Cauchy cuts. This generalizes Cauchy constitutive assumption for contact action. In my opinion, so-called Cauchy postulate is not a postulate, following the Greek meaning of the word postulate. It is actually a constitutive equation which limits the set of energies which can be considered. So we need to change at the very beginning this assumption. So the aim is to generalize Cauchy representation theorem to nth gradient materials. Now, for doing this, and this is another issue which I discussed with Gianpietro, you need to work with some mathematical details. With Gianpietro, we agreed that there is a general rule. My mathematics is useful, needed, and easy to understand. The mathematics of other people is useless, too abstract, and without applications. Think about this. Jupiter nos imposuit duas eras. The Jupiter gave us two big bags. Here are the problems, psychological problems of other people, and behind our own problems. I think that serious mathematics is always needed when you want to attack seriously a problem. And in this, with Gianpietro, we agreed. He was a little bit critical about the need of Gaussian geometry in this context, and he forced us to simplify it. So consider a surface which is more general than a regular one. It is a manifold embedded in three-dimensional space. You have regular curves concurring in points eventually, which we call edges. So think about a cube. The faces are the regular parts of the surface. The edges of the cube are concurring in the wedges of the cube. Okay. So what we are defining is a piecewise regular, orientable, and rectifiable surface embedded in E3, for which there exists a finite set of curves, C1, and a finite set of points, wedges. Of course, Antonio in Paris already found immediately an example of Cauchy cut which doesn't verify these conditions. We have to work on this. Okay, so I do not have the answer yet. The support of the boundary of S, here there is a delicate point. Everybody who worked in Poincaré style exterior algebra and exterior calculus knows that usually you have exterior derivatives, you have chains, boundary of chains. Okay. Here, our three-dimensional body has a topological boundary. This boundary is not the boundary in the sense of differential geometry. So the boundary which somebody calls border, I found a minority of books talking about manifolds with border, the majority of books talking about manifold with boundary. So think, the boundary of a body of our cube is the surface surrounding it. But the boundary of one edge, in this sense, of one face, are the edges. And the boundary of the edges, regarded as manifolds, are the points. So I'm happy that Massimiliano doesn't, this is our mathematics, so it is useful, right? So I use a clumsy notation, but I couldn't find a better one. Boundary of S, the partial derivative, the boundary of our cube is the surface. The boundary of the surface are the edges. The boundary of each edge are the 2 points. One point is calculated as many times as many edges are concurring in it, with a sign following the orientation. So when we count many times these edges depending on which phase concur in it. I call it boundary of S. If we consider them as a set of points, then we call union of gamma I. This is not complex, but is a delicate point. Okay? Okay, so here I am listing the definition, the points of a definition of a manifold with border or with boundary. There are charts on the boundary, the border charts, okay? And simply consider this. On an edge, you have a tangent vector, a normal n plus, a normal n minus, concurring in that point. In a wedge, you have all the tangent vectors concurring in that point, okay, of the edges concurring in that point, and you have all the normals of all the faces concurring in that point. So what is a shape of this animal, a local shape of this animal? In regular points, a shape of this animal is normal, Gaussian curvature. All gradients of Gaussian curvatures until regularity allows you. In an edge, you have the shape given by tangent vector, the two normals, Freinet trihedron, and all derivatives of these animals. Okay. Moreover, here we are considering edges in which only the normal jumps. You could consider lower order edges where, for instance, the first gradient of curvature jumps. And you will get lower order edges. Now, this differential geometry was, of course, known at the epoch of Middlin and Rivlin, but they did not apply it to their treatment. They considered only regular surfaces. So they could find only boundary conditions on these regular surfaces. Okay. Okay, here I continue. I want a vector, tangent vector, the length of which is 1, and I impose the condition of being normal. What is crucial here for what follows, then I hope we can proceed, is that on a given edge, you have an exterior normal to this boundary belonging to the tangent plane of the face concurring in this edge. And I'm calling this nu plus minus. If you remember, anybody among us was obliged to study such a thing while studying physics, second year, electromagnetism, and Maxwell equations. Okay, so this is the formalism which you need in that context. Before, in Italy, they decided that this is useless, so many engineers are not studying it anymore. So you get this and we represent each curve with a curvilinear coordinate starting from one wedge and ending to another wedge. Okay. So, roughly speaking, piecewise regular orientable and rectifiable surfaces in the particular conventional sense specified above are surfaces where the normal vector is defined in all points except those belonging to a finite set of wedges and to a finite set of regular curves. We call every connected component of the surface as a face. And here I start with introducing the tool which should make Gianpietro happy. Given a surface, or given a curve, or given, more generally, an embedded manifold, you can introduce Gaussian coordinates in the neighborhood of this surface. So you have coordinates along the surface and coordinates in the normal direction of this surface. If you call capital P the projector on the tangent plane, and you call capital Q the projector in the normal line, if you have a two-dimensional surface embedded in 3D. You can call P the projector along the tangent direction of a curve, then Q will be the projector in the orthogonal plane, and the game can be played in every dimension. Then you get this easy representation where I use Levi-Civita index notation for these tensor fields, and where the frame is unique for all points, so Cartesian orthogonal, and you must believe the result to the result of Gauss. You can find such a field, such two fields, not only on the surface, but also in the neighborhood of such a surface. And this trick is due to Paul Germain, at least in this context. Of course, these are very well known, but the application of this trick to Cauchy cuts and contact actions I found in Paul Germain's paper. Okay, so using the well-known divergence theorem, Luc Spivak is a famous book in differential geometry, you get this surface divergence theorem you can interpret easily. And when Wi is not projected before calculating the divergence, you get this extra term in which curvature appears. This is crucial for understanding the subsequent formulas. Okay, so I need to talk about differential geometry. I will not dare to talk about another mathematical tool which we need in this context, which is theory of distributions. I will say that the French tradition in mechanics led Salançon to teach exactly with these words to second-year students in engineering school, mechanics. Of course, you need a lot of serious mathematics for defining a distribution. A distribution, roughly speaking, is a linear continuous functional defined on a set of test functions. The delicate point is that you can introduce a metric inside in the set of test functions. However, the dual of this animal is not metrizable. You cannot find a matrix. And this makes all the story difficult. Okay. So, think about a continuous body moving in a reference configuration. Whatever could be the power expended by an action on a virtual velocity field. Everybody knows that power is linear in velocities. Do you believe that changing a little bit a velocity field, the power will change a lot? So it is clear that one wants to accept that power expended by internal or external actions with respect to a given body is a linear and continuous functional when defined in the set of test functions, where you have introduced Frechet topology. Now, the problem is to understand how distributions are made, which is the structure of distributions. So, the first postulate, let us call power. I will spend 2 minutes for telling that I've spoken with Lucio Russo about this. You know, Lucio is a very prudent person, so he gave me a homework. He told me, read the book of Lagrange about fluids. I will tell you, because of technological problems, formulas in Lagrange book are very similar to lines of tech. However, I do not know exactly which is the syntax of this. So up to now, I must tell you that this postulate has been formulated in this way at least by Cosserat brothers. So this is not at all new. But I strongly suspect that if you dig enough, you find it in Lagrange's book. So, the powers expended by the actions exerted on or exerted in a subbody are distributions in the sense of Schwarz. Of course, Lagrange did not know what is a distribution. No, you like to pull my leg. He knew what is a linear continuous functional. I don't know. Yeah. Okay. In any case, we assume that the support of these distributions are concentrated on the body you are considering. Okay? Now, Laurent Schwarz in '73 remarked that Paul Germain's paper is exactly of this year, the one written in English, proves that every distribution having compact support K can be represented as the sum of a finite number of derivatives of measures, all having their support included in K. This is an important property. Then you find a definition. A distribution is said to have order smaller than or equal to K if one can represent it as the sum of derivatives with order smaller than or equal to K of measures. And then there is even a uniqueness theorem. Every distribution having support included in a regular embedded submanifold, there are no edges and no wedges in Schwarz theorem, can be uniquely decomposed as a finite sum of transversal derivatives of extensions of distributions defined on M. So with these tools, we we want to attack the problem of determining how contact actions looks like in n-dimensional continua. Another of my fixation is Levi-Civita, as you may have guessed. Okay. I believe that Levi-Civita absolute notation is needed when you have tensors having many indices. You cannot avoid it. You need, okay, this is the integral which Gianpietro showed me when we were in Cisterna. You have a tensor saturated with the grad of a test function V. with some simple but lengthy calculations, you can decompose this integral as an integral of transversal derivatives only. V saturated with Q are transversal derivatives, at divergence of an operator applied to T, which is, and then divergence. So you decrease the tensorial order of this tensor, plus a term on the boundary in the sense of manifolds with boundaries of M. Okay, so you can write this lemma with a more compact notation, but then you are lost easily if you don't know the meaning of the symbols. So if you introduce divergence P0 of T equal to T and the alpha times iterated divergence of P in this form, then you get this representation formula. You have the integral of T grad kV equal to all these terms here, in which you have only orthogonal gradients, divergence, and divergence on the boundary of M. So you lower the order of differentiation by means of an integration by part. Of course, this cannot be true for orthogonal gradients. Now, we add something which is surely a constitutive equation, or maybe it could be proven by means of a trick of null, similar to Null's theorem. We assume that given a body, for every sub-body, power of internal actions can be represented in this way. So we are inspired by Schwarz's theorem, but Schwarz's theorem is not telling anything about the measure which is saturating grad lambda V. We assume it is absolutely continuous with respect to Lebesgue measure. And we assume that the same T lambda is good for every sub-body for a given body. So we have to be sure about this. Okay. There are many papers, which I will not discuss, which point out this point. Okay, so if you add the postulate, for the moment we call it Kossera postulate, the principle of virtual powers, you equate internal power to external power for every sub-body and for every velocity field, as written word by word in the paper of Paul Germain and in the book of Salançon, then you may represent the external power in terms of volume force capital E, surface force capital F0. Then you have double forces for delta equal 2. What is a double force? Something expending power on the transversal gradient of the velocity field. So you have just up to n-1 order forces on the surface boundary. Then you have 1 forces on the edge. You have up to n-2 forces on the edge. And then you have up to n-3 forces on the wedge. Now, I show you the implicit definition which generalizes Cauchy representation theorem. We can represent all these fields, surface fields, in terms of the T lambda we have introduced before. So, generalizing Cauchy representation theorem. So, this is capital T is defined in terms of divergence of T lambda estimated on the normal. Capital T double boundary is this other animal where P sigma is the projector on this regular part of the surface. Then F is zero force and F0 is, so F is F on the boundary, zero order. F on the boundary, jth order. And this capital T is exactly this one. So you see, it is rather complex representation. Then you have forces on edges, and then you have forces on wedges. So this remark is that all type of contact actions, so all type of forces can be represented in terms of bulk stresses. And if you like to write it in a complex way, the previous formulas allow you to introduce a functional on, depending on the shape of the Cauchy cut, the field of stresses you have in the body, and the index J, giving you contact actions. It is trivial to find that first order continua, for first order continua, this becomes Cauchy representation theorem. It is trivial to prove that for second order continua you get Germain's representation theorem, and we claim that we have found nth order representation theorem for any nth order continuum. Okay, so I am more or less in the time.